Hello everybody. So in this video we're going to continue with chapter 11, Integral Calculus, and it's the last section, 11.4, Modeling Linear Motion. So the first thing we're going to look at is displacement and total distance traveled. But before that, we're going to review something we saw before, and it is a fact that velocity, it's the derivative of displacement with respect to time. And it's a measure of how fast an object is moving or a particle is moving and its direction of motion relative to a fixed point. So normally that fixed point is the origin because here we're dealing with linear motion. So another important thing about velocity is that you need a direction and it's in relation to a fixed point. So velocity is a vector. Speed is the absolute value of velocity. And the speed of a particle is a measure of how fast it is moving, and it does not include direction. So speed is the magnitude of velocity, and very importantly, it is always positive. Acceleration, as you can see here, is the derivative of velocity with respect to time, and the acceleration of a particle is a measure of how fast its velocity is changing. Okay, so here we go with example 11.18, and it says the displacement of a particle on the x-axis relative to the origin is given by the position function s of t is equal to minus t squared plus 6t, where s in centimeters and t is in seconds. A, find a function for the particle's velocity, v of t, in terms of t. Graph the functions for displacement and velocity on separate axes. Okay, so basically all we have to do is the derivative, right? So for part A, the velocity function in terms of time is equal to the derivative of the displacement. So the derivative of minus t squared plus 6t, and this is easy to do. This is simply going to be minus 2t plus 6. So let's take a look at the graphs. What would they look like? And here they are. So notice that we have the position function as an inverted parabola, and we could see that through here, where the position with respect to the x-axis is given by this function here, and then the velocity, because it's the derivative of the displacement, is a linear function. Now, one thing very important to take into account is going to be this intercept here, because that means that at 3 seconds, there is velocity 0, and notice that here the velocity is positive, but then after 3, the velocity becomes negative, and velocity has direction, right? So that means that it had a positive velocity, it was moving in a positive direction or to the right, and then it stops at 3 and then moved to the left after 3 seconds. For part B, it says find the particle's position at the following times: t equals 0, 1, 3, and 6 seconds. Okay, so we have that the position function is s of t is equal to minus t squared plus 6t. So this is easy. All we have to do is plug in those times into the position function. So s of 0 is obviously going to be 0. So 0 centimeters. Then if we do s of 1, that's going to give us 5 centimeters. Then we do s of 3. So s of 3 is going to be equal to 9 centimeters if we plug this into the function, right? And then at t equals 6, we do s of 6, and that's going to give us 0 again, so 0 centimeters. Now this corresponds with the graph that we saw for the function, which was an inverted parabola. So you would have 0 at time 0, which was here, and then after 6 seconds, you would arrive back to 0. Very well, so now let's do part C. For part C, it says, Find the particle's displacement for the following intervals: from 0 to 1, from 1 to 3, from 3 to 6, and from 0 to 6 seconds. So let's understand, first of all, that displacement is not equal to distance. So what's the difference between displacement and distance traveled? So let's suppose that you go from point A to point B, and you do it in a roundabout way. So you go from A to B. So this curve would be your distance. That would be the distance traveled. So you traveled all that distance to get from A to B. But in reality, your displacement is this distance here. So the displacement is the actual change in position that you had from beginning to end, or in the interval. So it's a change in position. So that's what we have to do. So for the first time interval, which is from 0 to 1, what we have to do is plug in 1 and then subtract the position at time 0. So we did this before already, right? Remember that at 1, it was 5 centimeters. So 5 minus 0, and that means that the displacement was 5 centimeters. Okay, so the next interval is from 1, including 1, and to 3. So that would be the position after 3 seconds minus the position after 1 second. So we had calculated that after 3 seconds, the position was 9, and we know that at 1 second it was 5. So that means that the displacement was 4 centimeters. So notice there's a reduction in the amount. Okay, then how about between 3 and 6? So 3 and 6. So that would be S of 6 minus S of 3. And we had said that S of 6 was 0, right? So 0 minus 9, that means minus 9 centimeters, a negative displacement of 9 centimeters. And then finally, how about between 6 seconds and 0, right? So between 0 and 6. So this would be the total displacement of the particle between 0 and 6 seconds. So that would be S of 6 minus S of 0, and that's 0 minus 0, so 0 centimeters. What it means is that the particle returned to the original position on the x-axis. Okay, so for D, not B, let's correct that here. This is D, not B. It says, find the particle's total distance traveled for the following intervals: between 0 and 1, between 1 and 3, between 3 and 6, and between 0 and 6. So what's the difference between distance and displacement? Well, with distance, we have to do the absolute value of the displacement. So that's very important to remember. Now, if we want to calculate the distance between 0 and 1 second, the distance traveled, that would equal the absolute value of the difference in position. So that would be S of 1 minus S of 0, or the absolute value of that, I should say. So it's going to be the absolute value of 5 minus 0, and that's just 5. So 5 centimeters. The next interval is between 1 and 3. So again, the same process between 1 and 3. So absolute value of S of 3 minus S of 1, and that's going to be 9 minus 5, and that's 4 centimeters. So far no change from what we had gotten before. But how about between 3 and 6? So 3 and 6 seconds. So again, absolute value of S of 6 minus S of 3, and this is going to be the absolute value of 0 minus 9. And notice that now this is going to be considered a positive amount, right? So 9 centimeters. And then finally, how about the total distance traveled between 0 and 6 seconds? But before we do this, we have to take into account that there is a change in direction, right? And where was that? We said it before looking at the graph. Remember that the velocity was equal to 0 at time equals 3. So we have to take into account this in order to calculate this. That means that we would have to do first the absolute value of the displacement between 3 and 0 seconds. So S of 3 minus S of 0. But we also have to add the displacement between 3 seconds and 6 seconds. So S of 6 minus S of 3, and always the absolute value of this. So this is very important because there's a change in direction. Otherwise, we would get false results, right? So this is going to equal, and let's remember that S of 3 we found before was 9. So 9 minus 0 plus the absolute value of 0 minus 9. So notice that this is not going to equal 0 like we had found before with the displacement, but rather 18 centimeters. Okay, so next we're going to do example 11.19. But before that, we have to look at a note here. It says, given that v of t is a velocity function for a particle moving along a line, then the integration from a to b of the velocity function gives the displacement from time equals a to time equals b. Also, if we do the integration from a to b of the absolute value of the velocity, this is going to give us the total distance traveled from time equals a to time equals b. So we're going to apply this in this example. And it says the function for velocity, v of t, is equal to sine of pi times t, gives the velocity in meters per second of a particle moving along the x-axis. Part A. Determine when the particle is moving to the right, to the left, and stopped. If it stops, determine if it changes direction at that time. Okay, so when we want to find out if a particle is stopped, which is the first thing we should do, is that we have to solve the equation for when is velocity equal to 0. In other words, when is sine of pi times t equal to 0. So let's go to the unit circle and let's remember these intercepts with the x and y axes, right? So remember that this is 1, 0, this is 0, 1, negative 1, 0, and 0, negative 1. So let's remember that the sine function is y values, right? In the unit circle. So when is it 0? When is sine equal to 0? Well, sine is equal to 0, at pi, at 2 pi, at 3 pi, and so forth. So that means, so let's take this into account. So 0, then pi, then 2 pi, then 3 pi, then 4 pi, etc., right? Okay, so what does that tell us? It tells us that we have the solutions, right? Because t is going to be the number multiplying pi here. So that means that at t equals 0 would be a solution. T equals 1 would be a solution. T equals 2 would be a solution. And t equals 3. Not 4, we're not interested in 4 because that's out of the interval. We're talking about between 0 and 3 seconds. So that means that the particle stops at 0, 1, 2, and 3 seconds. So now we have to determine, it says determine if it changes direction at that time. Okay, so we're interested not in 0 because that's the starting point, and then 1 is when it stops, then it probably changes direction. At 2 seconds it stops, probably changes direction again, and at 3 seconds it stops. So we're interested in what happens here between 0 and 1, between 1 and 2, and between 2 and 3. So what we have to do here is pick convenient values and test for the velocity function, which is this one, right? So how about if we use between 0 and 1, we can use 1/2. So what is sine of pi halves? Remember that pi halves is 90 degrees, and sine of 90 is going to be 1. So that means that it's moving in the positive direction. The velocity is positive, therefore the particle is moving in a positive direction. It stops after 1 second. So what happens between 1 and 2? Let's use 3/2 or 1.5. But what is sine of 3/2 pi? Sine of 3/2 pi, remember that this is 1/2, 2/2, 3/2. So it's -1, right? Sine of 3/2 pi is -1. So there's a change in direction, right? It goes from positive direction, stops here at 1, and then negative. Then it stops again at 2. And let's see what happens between 2 and 3. So between 2 and 3, what's convenient to use? Well, 2.5, 5/2. And what is sine of 5/2? Well, notice that this is 1/2, 2/2, 3/2, 4/2, 5/2. So 5/2 really is just the same as pi halves, right? So that means then that the solution here to this, if we plug in 5/2, 5/2 pi, sine of 5/2 pi is 1. Therefore, it changes direction again at t equals 2 seconds. Okay, so for part B, it says find the particle's displacement for the time interval between 0 and 3 seconds. Remember that the displacement is given simply by the integration of the velocity from A to B. So in this case, we would integrate from 0 to 3, and the velocity function, which is simply sine of pi t dt. And notice that this is going to be minus 1 over pi cosine of pi times t, and this is going to be between 0 and 3. So from here we're going to get minus 1 over pi cosine of 3 pi minus, parenthesis here, again minus 1 over pi times cosine of 0. So if we do the math here, this is going to give us, let's do it here. So what's cosine of 3 pi? Remember that 3 pi is going to be simply here, right? 3 pi. Remember that if we go pi, 2 pi, 3 pi. So cosine of pi is the same as cosine of 3 pi, and here it's -1. So this is going to be minus 1 over pi times -1, and this minus, so plus 1 over pi times cosine of 0, but cosine of 0 is 1. So this times 1, and notice that from here, we're going to get 2 over pi as an exact answer. If you plug that in the calculator, it is going to be approximately 0.637 meters to 3 significant figures. So now we're going to do part C, and it says find the particle's total distance traveled for the time interval from 0 to 3. So here we're going to use this second fact, that the integration of the absolute value of the velocity and that time interval is going to give us the total distance traveled. So that means that we have to integrate from 0 to 3, but this time for the absolute value of sine of pi times t dt. Okay, now if you do this in the calculator, it's going to do it appropriately. It's going to do it correctly. But if this is, say, a paper 1 question, you're going to have to do this by hand, and you have to take into consideration the different time intervals. What time intervals? Well, the ones where the particle stops. So remember that the particle would stop, first of all, at 0, where it starts, then after 1 second, 2 seconds, and 3 seconds. So that means that we would have to integrate this separately. we would have to integrate from 0 to 1 for the absolute value of sine of pi times t dt. And then we would have to add to this the integration from 1 to 2 of the absolute value of sine of pi times t dt. And then, okay, absolute value. So let's not forget that there, absolute value. And finally, plus the integration from 2 to 3 seconds, again, of the absolute value of sine of pi t dt. Okay, so this will equal absolute value of 2 over pi for that first integral, plus absolute value of minus 2 over pi, plus the absolute value of 2 over pi. Okay, so this is going to give us exactly 6 over pi, which is approximately 1.91 meters. So this would be the total distance traveled. Notice that if we had not done this with absolute value, this would have been negative. It would have canceled out with this, and then we would have gotten the same answer. But because we're doing absolute value, we're going to make this into a positive amount. So that adds up to get the total distance traveled of 6 over pi, which again is 1.91 meters. Very well, so now we're going to do example 11.20. And it says, the motion of a falling parachutist is modeled as linear motion by considering that the parachutist is a particle moving along a line whose positive direction is vertically downwards. The parachute is opened at t equals 0, at which time the parachutist's position is s equals 0. According to the model, the acceleration for the parachutist's motion for t greater than 0 is given by a of t is equal to negative 54 times Euler's number to the power of minus 1.5 t. So part A. At the moment the parachute opens, the parachutist has a velocity of 42 meters per second. This is important. Find the velocity function. So they want us to find the function for velocity of the parachutist for t greater than 0. And then it says, what does the model say about the parachutist's velocity as t increases or as t tends to infinity? Let's remember that if we have velocity, the derivative of the velocity function is equal to acceleration. Therefore, the inverse of this is true. We can find the velocity by integrating the acceleration function. So that's what we're going to use here. That means that in order to find the velocity, we have to integrate this function here, minus 54 times Euler's number to the power of minus 1.5 t. And this is going to equal minus 54 times Euler's number to the power of minus 1.5 t. And then in order to integrate this, remember that we need to have minus 1.5 dt. And since we have to multiply by this, we also have to divide by it. So this divided by minus 1.5. And then this is pretty straightforward because this will give us 36 times Euler's number to the power of minus 1.5 t plus a constant c. So we still have to find this constant in order to have the velocity function. But we have some information that's going to help us. And it says that at the moment the parachute opens, so that's t equals 0. So when t equals 0, the velocity is equal to 42 meters per second. So that means that 42 is equal to this when time is equal to 0. So let's put that here, when time is equal to 0. So notice that this would become 1 because e to the power of 0 is 1. So that means that 42 minus 36 is equal to c. Therefore, c is equal to 6. So that implies that the velocity function is then going to be 36 Euler's number to the power of minus 1.5t plus 6. So that would be the first part of the question. So the next part says, what does the model say about the parachutist's velocity as time increases? So that means that what is the limit of this function, the velocity function? So let's rewrite it as 36 over e to the power of 1.5t plus 6. What is the limit as t tends to infinity? So as t increases, so will this part, right? The denominator of 36. So that means that this will tend to 0. Therefore, we're going to be left with 6. So that means that as time increases, the velocity tends to stay at 6 meters per second. So for part B, it says, find the position function of the parachutist for t greater than 0. So the position function is equal to the integration of the velocity function. In other words, we would have to integrate what we just found. So we have to integrate for 36 times e to the power of minus 1.5t plus 6. So we have to integrate this in terms of time. So this is going to be, if you do the math, it's going to be minus 24 e to the power of minus 1.5t, and this plus 6t, and plus a constancy. But again, remember that we had information about the position. Where was it? So it says that the position is 0 at time equals 0. So that means that this equals 0, position is equal to 0 when time is 0. So S of 0 is 0. So that means that this is equal to 0 when time is 0. So notice that this is going to be minus 24 e to the minus 1.5 times 0 plus 6 times 0 plus c. So notice that this is going to equal 1, this is going to equal 0, and then we move this to the other side, we're going to get that c is equal to 24. So that means that we have the position function. The position function would be minus 24 e to the minus 1.5t plus 6t plus 24. So in the next slide, we're going to talk about uniformly accelerated motion. Motion under the effect of gravity in the vicinity of Earth or another planet is an important case of rectilinear motion. This case is called uniformly accelerated motion. So if a particle moves with constant acceleration along the s-axis, and we know the initial speed and position of the particle, then it is possible to have specific formulas for the position and speed at any time t. So basically here they're showing us how we can derive formulas for velocity and position based on the fact that you have uniformly accelerated motion. So what does that mean? Well, if the acceleration is constant, then we can say that a of t is equal to a, that the velocity at time 0 is v sub 0, or initial velocity, and that the position at time equals 0 is s sub 0. So notice that if we want to get the velocity, we integrate the acceleration. So if you integrate for a, you're going to get a times t plus a constant. But since we know that at 0, velocity is just v sub 0, so then we just plug that into the formula, and we end up with this here, which is the classical physics formula for velocity when you have uniformly accelerated motion. Then we can do the same thing for position, because then we would have to just integrate the velocity function, right, that we just found. So notice that if we integrate this here, which is this velocity function that we just found, we're going to get 1/2 at squared plus initial velocity times time plus c. But then again, because we know that the initial position is s sub 0, this is going to be the derived formula for position in classically uniformly accelerated motion. Then there's the case when this is applied to free fall, where we know that the acceleration is the force of gravity, which is 9.8 meters per second squared. And we can see that it's a simple substitution for A, substituting it for G, which again is the acceleration due to the effect of Earth's gravity. Okay, so now we are going to do example 11.21, which will be the last one on this video. And it says, a ball is hit directly upwards from a point 2 meters above the ground with initial velocity of 45 meters per second. How high will the ball travel? So that means that the ball is at a height of 2 meters. When it is hit directly upwards, that means that it goes up, and then due to the action of gravity, it's going to decelerate, stop, and then come back right down. So what we need to do is find how high the ball traveled. Okay, so let's remember what these functions are for velocity and for position, because we're going to need both of them in this case. So let's remember that velocity as a function of time is equal to acceleration, which in this case would be gravity. So gravity times time plus initial velocity. So we already have some of this information. We know that gravity is equal to minus 9.8 meters per second squared. So this times time plus the initial velocity, which they give us in the problem, 45 meters per second. Then we have the position function, right? The position function is the integration of this function here. So notice that we would get minus 4.9 t squared plus 45t plus the initial position. But we already know what the initial position is because it's 2 meters. So we can substitute that in here, and let's just write it as 2. So this is a function we need to solve, but it's a function in relation to time. So we need to find how much time, what time it took for the ball to reach a maximum point. But that's easy using the velocity function because we know that at the maximum point, the velocity is going to equal 0. So what we have to solve is minus 9.8 t plus 45 is equal to 0. So that's going to be minus 9.8 t is equal to minus 45. So t is going to be minus 45 divided by negative 9.8, and this is approximately 4.6 seconds. So once we have the time, we can plug that into the position function. So we will do s of 4.6. So that's going to be minus 4.9 times 4.6 squared plus 45 times 4.6 plus 2. And if we plug that into the calculator, it's going to give us 105.32 meters. So that means that the ball reached a height of 105.32 meters with respect to the ground.